All right, let's keep going. In chapter 18, aromatic substitution reactions. So we are going to be talking about adding things to benzene, substituting the protons on benzene, right? Benzene C6H6 has 6 carbons and 6 hydrogens. Now we are going to be substituting those hydrogens, and we're going to be talking about how we can build up our benzene ring. Always want to start with some fun, right? There's benzene waving to ya. Stubborn benzene, no, 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 no. Santa benzene, ho, 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 ho. Alien looking benzene. Yeah, that's weird. Yeah, it's funny. Okay, let's keep going on, right? We know that benzene does not react the exact same as typical alkenes, all right? This is where electrophilic aromatic substitution comes into play. We are going to be learning different ways to react benzene. Yes, benzene can react, it just takes a little bit extra. What's the extra? Well, halogenation does not work, but halogenation with a catalyst such as iron or a extra piece of the puzzle, the substitution does occur, right? And so this is where electrophilic aromatic substitution came to be. Also called EAS for short, the aromatic proton is replaced by an electrophile, and the ring acts as a nucleophile. Okay, so that's really important to understand that the benzene ring in these reactions will be acting as a nucleophile. We will see these 6 reactions in this chapter. Bromine and chlorine are essentially the exact same, but all of the electrophilic aromatic substitutions are very similar. Notice how the aromaticity of the ring is preserved at the end of the day. So, bromination of the alkene from chapter 8, Br2 was functioning as the electrophile. Why? Because it was polarizable, right? A Lewis acid catalyst, though, is needed to make Br2 electrophilic enough for our benzene ring, right? So this was what we did before. Bonk, bonk, and yes, we had back bonding occur, right? But this essentially was the electrophile and the pi bond was the nucleophile. Now, why adding iron worked is because iron with Br2 will make FeBr3, and that is our Lewis acid catalyst that we need to activate the electrophile Br2, okay? So we will see that FeBr3 is going to be added to our reaction. What happens first is we need to prepare the more potent electrophile. We need to prepare that reactive electrophile. How we do that is from some Lewis acid and base chemistry. Now, we didn't do a lot of Lewis acid base chemistry before. If you remember, it was way back in chapter 3. However, what we're looking at is a nucleophile attacking an electrophile here. Br is going to attack the iron. Transition metals are great electron acceptors because they have the d orbitals. There's some extra bonding going on in them. And so what this does is it actually makes our really, really potent catalyst. You can use this guy, or you can go one step further and say, woo, there he is, Br plus 1. That is crazy, right? I'm going to go ahead and use this whole guy right here to go forward. The FeBr5 minus 1 or minus plus this guy, right? We're going to say, okay, what's going to happen? Well, carbon can pick up that outer bromine, the one that was the most electrophilic position, and kick off FeBr4 minus 1. Now, what that generates is a new carbon to bromine bond. All right, I'm going to highlight it. New carbon to bromine bond. It also breaks aromaticity. The aromatic ring attacks the electrophile, and a sigma complex is the intermediate that is formed. It is a resonance stabilized higher energy intermediate. How is it resonance stabilized? I'm so glad you asked. The extra p orbitals are there to resonance stabilize this sigma complex. Now, the Br on the other, on the iron, the leftover bromine on the iron is actually going to do an elimination reaction to restore aromaticity. The second step of this reaction, if you consider the nuke attack as the first step, right, add the bromine, then we have to eliminate the hydrogen to complete the substitution. That is the exothermic step because it is reestablishing aromaticity for us, all right, and completing that substitution. From that, we get HBr, and FeBr3 is reformed, right? It's a catalyst. Skipped one. Addition reactions to the aromatic ring would be endergonic. So we only do substitution reactions, right? We're not going to add two halogens. Don't do an addition reaction. That would not be fun. We are going to see that the first step, adding the bromine, makes the sigma complex, the higher energy non-aromatic intermediate. And then doing the substitution by removing the proton will reestablish aromaticity. And that is what is exergonic. All right, with halogenation, we can also use aluminum, right? Aluminum tribromide is also okay to be a Lewis acid. It does the exact same thing as iron did. So FeBr3 or AlBr3, totally fine. Chlorine does the same thing, right? So Cl2 with aluminum trichloride or iron trichloride is A-okay as well, right? They do the exact same mechanism. Using F2 or I2 doesn't really work well. Fluorination, like always, is just way too violent to be practical. And iodine is really, 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 really slow. Back in my undergrad, I did try and develop I was part of the synthesis of a anti-cancer drug that we were trying to fluorinate, right? So we started with bromination, and then we chlorinated it, and then we substituted with fluorine, right, to see if the reactivity would be better. It was, but bromination is slow enough, y'all. Don't even think about iodination. That's way too slow. Iodine, not good. In fact, all electrophilic aromatic substitution mechanisms do the exact same two steps. We'll see a pi bond react, attack an electrophile. The sigma complex is all happy hunky-dory, stabilizing our high energy intermediate. And then the base, whatever, comes back and does a proton transfer to complete the substitution reaction. So we get an H being substituted by a common electrophile. All right. Next one, sulfonation. Sulfonation occurs by using SO3 as the electrophile and H2SO4 as the acid catalyst. Not a Lewis acid catalyst, now it is a actual proton, right? Bronsted-Lowry acid catalyst. Fuming H2SO4 is what contains SO3 gas. So you can see one of two things over the reaction arrow, SO3, H2SO4, or you can see fuming H2SO4. That means the exact same thing. And what we get is sulfonation to occur. We add SO3H to the actual molecule. Now, SO3 is a really potent electrophile. The sulfur atom itself has a significant partial positive charge due to inefficient overlap with the pi bond. So the SO bond itself has a significant single bond character already. And so what we see is our pi bond will react, boop, add on the sulfur, and kick up a pi bond onto one of those oxygens. We still have the sigma complex, right? Still having that beautiful resonance occur. And then we're going to use water as the idea of the base. We don't have hydroxide because we're in water, we're in H2SO4, and that would make H3O plus, and we can see that last little proton transfer is because we need to protonate the SO3 that was added, right? SO3H, so that we can take away that negative charge and make it neutral with the extra workup, okay? Sulfonation is a sensitive reagent but to concentration, so it is a reversible process. So if you can use concentrated fuming H2SO4 and actually make the SO3H on the benzene. If you add it to dilute H2SO4, you can actually reverse the process. This is going to be helpful when we talk about it a little bit later on in the chapter for synthesis techniques. All right, so nitration, again, same idea. HNO3 is going to be the source of the electrophile. H2SO4 is going to be used as the acid catalyst. You can think about H3O+, just like we used before. But it is believed that the nitronium ion, NO2 plus 1, is the active electrophile. Let's talk about how that is made, okay? So we have NO3 over here, just in case you didn't know what HNO3 looked like. There it is, HNO3. I know we don't often draw these Lewis structures when we use the acids in the lab, but there it is. What happens is the oxygen of the hydroxide on HNO3 is actually the most basic molecule. And the reason for that is the other oxygens are stuck in resonance. What that creates is a water-leaving group. And so the other oxygen will create an oxygen-nitrogen double bond and kick out water. There is our active electrophile. NO2 plus 1. The nitronium ion is highly electrophilic, so we can take it straight into our reaction with benzene. Benzene will attack the nitrogen and kick up an oxygen lone pair. That again creates a sigma complex, lots of fun resonance, so much rejoicing, and then water, right, which was produced in the preparation, is going to do the deprotonation, the proton transfer, okay, to reestablish aromaticity. Again, nuke attack the electrophile with benzene, sigma complex, joy, and then proton transfer that to finish. The nitro group is actually really interesting because that NO2 group, I'm going to draw it out here just so that we can see what it would look like. It has an oxygen with a negative charge and a nitrogen with a positive charge. Overall net neutral, right? But it is a reactive substituent. It can be reduced to form an amine using iron or zinc with HCl in an acid solution. And then NaOH is just there to make sure that we are neutralizing that nitrogen, because that nitrogen in an acid would form a protonated amine. So the NaOH is just as a little workup to make sure that we can have a neutral final product. Now, combining then all of these reactions, you can install the amino group onto a benzene ring, right? So we will be able to see lots of different uses for the amine at the end of the day. But you can start with nitration and then do reduction in the final two steps.